Hi, in this video I'm going to talk about extracting information from textual data. Textual data is a very prevalent form of data. You cannot find any field of science or in industry that is not in need of processing, understanding, or utilizing their data which is in the form of text in one way or the other. And you should also keep in mind that we are now producing a massive amount of textual data all the time. So at the end, it is no human or group of humans' job to perform all the tasks that I already said. The tool for doing all this sort of processing, understanding, utilizing the textual data is natural language processing, or in short NLP. And this is the way to process most of this form of data. NLP is like a combination of a lot of fields. There is machine learning in there, there is artificial intelligence in there. Natural language processing combines a lot of those fields, but also has a very unique feature to it because we are working with the text data, which is very different from the other kind of data in the sense that for the other kind of data, we usually use machine learning, which is mostly quantitative and not qualitative, and this is the difference basically. In natural language processing, we're dealing with text data. And when NLP is useful, where are the situations that we can use NLP? I give you one example. For example, we are utilizing sentiment analysis by having NLP. And this is one of the big area when we are, for example, trying to have the review data from different kind of places, the feedback data, and then analyze to see how different they are, how the feedback. Basically, in a sense, we want to get the essence of the feedbacks we're getting, not necessarily the words that are written, the emotions, the sentiments that behind that. So that helps us, for example, in a business setting, to understand how our product is received. Do we need to change anything, or people are generally happy with it? So these are one of the situations in the chat, in any sort of text data that we're getting, and we're we care in a sense about the emotions, the reactions that we're getting from the other people. The sentiment analysis comes in play. One thing that you need to know is that in this course we will not go deep into natural language processing, but you're going to hear more about this topic in artificial intelligence or machine learning course in the other periods. In this course, we will, to some extent, discuss how to provide a workable starting point for an NLP model. And what do I mean by that? In order to make sure that we have a very realistic NLP model, and to make sure that we are doing everything right from the beginning, we need to do a bit of noise cleaning. We need to have a clean data as the starting point from our models, a good baseline for the model. And why we are doing that? The fact is, human languages are very complicated. When a person talks in a language, us as the humans quickly understand what they mean. In a sense, we classify the intent very quickly and understand whether there's a sarcasm underlying the thing that they are saying, or they are just literally saying what they mean. It is easier for us as human beings, not necessarily always. This is what we learn during a life with a lot of hidden cognitive tricks. But for machine learning algorithm to do something like that is really difficult to handle. So that is why we need to take care of the data that we are feeding at the beginning to the model. We need to clean the data. We need to do a lot of pre-processing. One way to do this beginning step, this pre-processing step, is that we need to tame the complexity of the language. And to do that, we do something called feature engineering. Feature engineering is a process of selecting and transforming some of the variables in order to create a model for a machine learning system. What you need to know is that feature engineering is not only based on a set of predefined rules, but also it has a very strong basis of understanding the problem domain and having a good grasp of the end goal, in the sense that we, for example, need to know, if we have enough domain knowledge, what are the impactful factor, let's say, to underline the emotions behind somebody's words. What are the keywords? What are the word roles that design that? And we also need to know at the same time what is it that we want at the end. So we need to know a bit these links and connections to be able to do some sort of feature engineering to pick the things that are more important for us and we think are going to be more impactful in the accuracy and in the efficiency of the model we are building. So why do we need feature engineering? Basically, the machine learning algorithms could not work on raw text data the way we are reading it. Human can understand the text data by reading it, but robotics could not do that. They only understand numeric representation of the actual data. So you do need to numerically represent the text to be able, for example, to vectorize it. And you probably have heard already in some other contexts something like called one-hot encoding, and this is what we are having here. As the name suggests, the one-hot representation starts with a 0 vector and the set of and sets as 1 the corresponding entry in the vector if the word is present in the sentence or document. Consider the following two sentences, for example. Time flies like an arrow, fruit flies like a banana. So we want to tokenize the sentence. First of all, we ignore the punctuations and then treat everything as lowercase. So we will have a vocabulary of 8 words. Time, fruit flies like an arrow, and banana. So we can represent each word with an 8-dimensional one-hot vector. And this is what you're seeing. The collapsed one-hot representation for a phrase, sentence, or document is basically a logical OR of the one-hot representation of its elements. It's a word that makes it a sentence. Let's go back to NLP and think about, again, why data processing for textual data is important. And I want here to give you the challenge, one of the main challenges we have, and this is the difference between syntax and semantics. So what do we mean by syntax, and what do we mean by semantics? Syntax is the grammatical structure of the text. Where should be the noun, where should be the verb, where should be the object. But semantics is the meaning that is conveyed in the text. Now, here is an example. The guy is saying, call me a cab, and the girl say, probably it is synthetically true. It has all the components. It has the object, it has the verb, it has the noun. But the meaning that is transpired to the girl is that my name is a cab, and then the girl is going to say, okay, you're a cab, which is funny in a sense, and this is not the accurate meaning that the guy wanted to convey. So if the words are not in a correct structure of a combination of words, then we won't get any meaningful thing out of it. And you should also remember that there's a lot of combinations of linguistic heuristics and the whole process of the grammar that one needs to understand in order to make sense of sentences. And this is where the difficulty lies. That is why we do feature engineering. We do, to some extent, simplify everything for the machine to understand. So let's see what are some of the steps that we can do in order to achieve the proper set of data that we require? What are the steps that we can do for feature engineering? One thing that we can do is part of a speech or pose tagging. In the next few minutes, I will try to explain how we can achieve it. In corpus linguistics, part of speech tagging, also sometimes called grammatical tagging or word category disambiguation, is the process of marking up a word in a text as corresponding to a particular part of a speech. And part of a speech, as you, I'm sure, know, could be something like pronoun, verb, nouns, determinants, and many other things. So another thing that you also need to know, that part of a speech is not necessarily defined independent of the context. Basically, it's tagged in relationship with the adjacent or the other words around that particular word in a phrase, sentence, or paragraph. Now let's try to see what I mean by that. Why the context or the words surrounding that specific or particular word that we're tagging is important. Let's consider this picture, this sentence. Time flies like an arrow. You can get various meaning, and the picture here is actually quite expressive. You can see what from the same sentence, depending on how you look at it, you could get different meanings. For example, time flies like an arrow. It is different when you consider time as a noun or you consider time as a verb. The first two sentences is describing the time in the sense that minutes, whatever, hours. So the first one is saying that the time is quite fast, and that's like an arrow in one direction. The second point is still a noun, but it is considered as a pack of nouns in a sense. Time flies. Now there are some creatures, as you see in this figure, that are called time flies, and they are similar to an arrow. And the last one is basically an imperative sentence. It's asking somebody to time when the flies are like an arrow. So, I mean, now it's very complicated what I said, but at the end, I am sure you get what I mean, that one sentence could be interpreted on many different way, and as such, the part of a speech might vary for each word in the same sentence. As I said, this example shows different way of doing pose for one single sentence. And the tags reveal a lot about the word and its neighbors. So you can say that knowing whether a word is a noun or a verb is not hard, but understanding what is its role in a sentence is much more complicated. So now let's get to different ways of doing pose tagging or part of a speech tagging that we have. One of these ways is called rule-based tagging or rule-based pose tagging. This is one of the oldest approaches to pose tagging. It involves using a dictionary consisting of all possible pose tags for a given word. If any of the words have more than one tag, handwritten rules are used to assign the correct tag based on the tags surrounding the word. For example, if preceding of a word in an article is an article like the, and then the word has to be a noun. For example, the example I have here, a book. When we have the book and we see the A is coming before that, we know it is a noun we're talking about, not a booking system. I mean, not that we want to book a ticket or something like that. So what it happens in this form of tagging is that the algorithm gets all possible post tags for one individual word. In this example, a book, it's A is an article, book could be a noun and or a verb, and then the algorithm uses the rules to assign correct post tag to each of them. And then A is still an article, but you can see based on the context, book is going to be the noun. So post tags will be A article, book, noun. Similarly, various rules are written or machine learned for other cases. Using these rules, it's possible to build a rule-based post tagging system. And it is, of course, reasonable, logical to do such form of tagging, but one thing that you need to remember is that this is a manual task, it is challenging, and it is not really scalable. You cannot do a whole body of literature and do all this tagging of that. There's also another way of doing the tagging, and that is called a stochastic tagging. A stochastic tagger is a supervised model which uses frequencies or probabilities of the tag in the given training corpus to assign the tag to any word. These taggers altogether rely on the statistics of the tag occurrences. Basically, what is the probability of book, in the previous example being a noun, what is the probability of book being a verb, and whatever probability is higher than that is assigned to the word. So there are two ways of doing the stochastic tagging. One is word frequency. We basically look through the whole corpus and see what is the most assigned tag to this word. For example, if book occurs 10 times and 6 times a noun 4 times as a verb, then it's going to be a noun. There's also another way, because at the end, this word frequency is not very reliable. It doesn't mean that if something comes more, this is always the proper tag. So tag sequence frequency, and in a sense, it has these hidden rules that we talked already in the rule-based thing before, and I tell you what I mean by that. So the best tag for a word is determined using the probability of the tags of n previous word. For example, it considers the tags for the words preceding book. And although this approach provides better results on a word frequency, it may still not provide the accurate result. And tag frequency is also referred to as the n-gram approach. And n-gram is something that we're going to discuss a bit in more detail. But before getting to the n-gram, let's see what are some of the challenges that we have here. For example, one of our main challenges is that a single word could have different meanings. For example, think about bear. I have seen a bear, and in this context, bear is an animal, but if I try hard, my efforts will bear the fruit. Here, bear is a verb, and it has nothing to do with this large mammal. It's basically meaning that it will pay off. All my efforts is going to pay off. So, as you see, still this hidden understanding, the context is also very important. Now, there are some algorithms to facilitate tagging, and we are going to briefly discuss some of them. And one of them is shallow parsing or chunking. So already we talked about post tagging to give assign part of speech to each word. For example, in this sentence, the first boxes, the inner boxes that you see, we have the pronoun, we have the verb, we have the determinant, we have the adjective, and we have the noun. So this is the first basic tagging without considering the context. Or this is what we are sometimes referring to as the tokenizing. So each word has a token here, as you see in this example. But the next step, doing it a bit more complicated and much more useful, is actually to think about chunks of words or chunks of sentence. So now we is a chunk, and then the yellow dog, this is something that typically comes together in this sentence actually. This is a chunk that they are connected to each other. They are describing one way or the other the same thing. So this is what we are calling shallow parsing or chunking. And this is where it is somehow doing a compromise. We don't want to stay on this very naive level of only assigning each word one token. We want to know a bit more, we want to get some general information, but we don't want to do some deep algorithmic computation. So that is exactly where we can use shallow parsing or chunking. We want to get more information, we don't want to do something very complicated, deep, we are going for shallow parsing or chunking. And what's the difference between portable speech stacking or chunking is, as you see, these green things here are my part of speeches, but then chunking are putting them together, getting more information out of it. The lazy dog, the brown fox, these are the chunks that we have. And then we have larger chunks, like one sentence is also a chunk. The brown fox is quick, he's jumping over the lazy dog. So all these are different chunks that are giving us some extra information. Another way of tagging is called named entity recognition, or NER. Named entity recognition is one of the key entity detection methods in natural language processing. Named entity recognition is an NLP technique that can automatically scan the entire article and pull out some fundamental entities in the text and classify them into predefined categories, like organizations, like quantities, like percentages, like people's names, companies' name, geographical locations, amount of money, name of the events. In simple words, if I want to tell you what NER does. NER is the process of detecting the named entities such as names, location, names, company's name, etc. from a text. It's also known as entity identification or entity extraction. And NER can help us extract key information to understand the text, or just to use it to extract important information, to use it to store it in a database. Sometimes we don't want to. We know what is a text that we're dealing with, so we really don't need to read every line to get the context and everything. We know there are several organizations in this text. We just want their names. For example, it's a contract. We want to get the name of all parties in the contract. We know different countries are involved. We just want to get the name of geographical location on that text. So this is where we are using NER, and it could be used in chatbots, content analysis, consumer insights. There are lexicon approach is basically relying on a knowledge-based ontology where all the terms related to a specific topic are stored, and they are grouped in so that you can understand the differences between categories. And basically what system does is going to look in the whole ontology to see what matches the named entity. The problem with this approach is that this approach doesn't work to extract new words which are not in the lexicon. So if there is something that the lexicon has no information about, basically that is a dead end. And some examples are lexicons of cities, states, countries to recognize location in a data. Another approach is called rule-based approach or rule-based systems. And in this approach, there's a series of grammatical rules that you have. And for example, you're expert on a subject matter and you know how things are patched together in that specific text. So you can put it basically out for the system to go through and see if these words are together. So this is the noun, this is the verb, this is the object. It can get results of high precision but low recall. And one thing that you need to remember is that defining rule takes a lot of time and it's also very domain specific. So whatever system you're building with this approach is not generalizable to the other fields. For example, a model to extract legal terms is something that could benefit from rule-based approach. And in this method, in this example, you will basically manually tag tokens of legal methods, cases, and processes. And one final approach, something that you probably have heard of, is the machine learning based systems. What happens here is that we build an entity extractor, a model that could extract the entities. And by that, I mean, we build a machine learning model, we feed it a huge volume of annotated clean data, and by going through that, the model learns what is the role of each entity, what is the name for each entity. This is, of course, something that we may want to use, and it may be very attractive, but one thing that you need to remember is that it needs tagged and clean training data, which could be cumbersome in many situations. So one example is to build a model to extract legal terms, and then you need to manually tag tokens of legal methods, cases, and processes. Okay, so now let's get to n-grams that I already promised a few slides back. Now let's talk about n-grams. First of all, let's see what the term n-gram means. Well, this is probably the simplest part. Basically, n-gram is a sequence of n words. Here, unigram in this sentence, this is a sentence, all of them are one unigram. If we want to have more, we have bigrams, a combination two words, consecutive words in a sentence. This is a sentence, all of them are the examples of bigrams. And trigrams, this is a sentence or two trigrams that we have in this sentence. We could increase the number of n's as much as we want. One thing that we do is to assign probabilities to n-grams. And what do I mean by that? If we assign a probability to an occurrence of an n-gram, or the probability of a word occurring in a text, for a sequence of words, for example, what is the probability of having the lazy dog, we will get some useful information out of it. And what that is, for example, it can help in deciding which n-grams can be chunked together to form single entities. For example, San Francisco, for example, high school. These are the words that could be chunked together. It could also help making next word prediction. For example, let's say, please hand over and what that could be an assignment, test, paper. So somehow, if you know what the context is, you can predict the next word. It can also help to make a spelling error corrections. For example, if we have drink coffee and the coffee is with one F, we know what the correct word is. So as you see, these probabilities could give you huge potential in the NLP domain. And going back to the word prediction, the question may be that how these predictions happens. Basically, the prediction is based on the n-1 previous words. If we are dealing with a bigram, the prediction is happening only based on the previous word, But if it is a trigram, 2 previous words, and so on and so forth. And what you need to remember is that generally bigram's model works well, and it may not be necessary to use a trigram models or higher degree of n-gram models. Okay, so enough of theory and explanation and talking. Now let's get our hands a bit dirty with the hands-on practice. So see you in the next video.